On page 248 of the textbook, you will find the author's procedure for graphing a function y equals f of x that puts together all the concepts we've talked about so far in chapter 4. We're first supposed to identify the domain of the function and any symmetries the curve may have. Well, by identifying the domain, we'll know where the graph should be. We'll also know where my critical points and points of inflection should live, and it will help us know if they're asymptotes or not, or holes. By determining the symmetries, if I know it's an even function, well, if I graph half of it, I know what the other half looks like, and the same thing if I have an odd function. I'll then compute two derivatives so that I can then do the first derivative test and the second derivative tests to determine where my curve has critical points and might have mins or maxes, where it's increasing and decreasing, and where the points of inflection in regions of concave up and concave down are. I'll identify any asymptotes, remembering that in this class, because it's a calculus class, we'll justify asymptotes with correct limit statements. And then step 7, we'll find the x and y intercepts and put that together with everything we've done so far to get a good graph of the function. Let's use that procedure to graph y equals the natural log of x all squared. Now, as I go through this, I might not go in exactly the same order your author did, but I promise I'll do all of the things. I do think we should write down the domain of this function first. Because the natural log is what is on the inside, its domain is the domain of the entire thing, which is just from 0 to infinity. Those are the only x's that can go into the natural log. So let's compute two derivatives. I have to use the power rule and the chain rule. Tell me that the first derivative is 2 times the natural log of x all over x. Okay, so now let's take a second derivative. The bottom gets squared, and then I have the bottom times the derivative of the top minus the top times the derivative of the bottom. Simplify that, and I'll have 2 minus, wrote the wrong thing there, the derivative of x is 1, and I'll have 2 minus 2 times the natural log of x. All right, let's see if I can find any critical points. Well, the natural log of x is equal to 0 at 1. So 2 times the natural log of x is also equal to 0 at 1. Remembering that a fraction is equal to 0 where the top is, that's my critical point. The first derivative is not defined at 0, but that's not in my domain. So I only have that one critical point, and I'm going to go on and draw my first derivative number line. All right, so I want to analyze, I want to remember that this domain started at 0, so I don't need to go past 0 at all. So I need to analyze this and see where my function's increasing and decreasing. So maybe I think about plugging in something like 1/2, and maybe I think about plugging in something like 2. The natural log of a number smaller than 1 is negative. So this will be a negative over a positive. So my function is decreasing until I get to x equals 1. The natural log of something bigger than 1 is positive. That'll be a positive over a positive. So then it increases. Okay? So now we're to my second derivative where I want to know any values where my function might change sign, or my second derivative might change sign. So I need to know the values where my second derivative fails to exist or is equal to 0. Well, again, the second derivative doesn't exist at 0, but that's not in my domain, so I don't need to worry about it. So I just need to set the top equal to 0. And adding this to both sides, I have 2 natural log of x equals 2, which means the natural log of x equals 1, which means x has to equal e. All right. So I had a critical point in the first derivative of 1. The only place I need to worry about maybe having a point of inflection is at x equals e. So I need to think about plugging in values to try to see whether my second derivative is positive or negative. The number that's less than e I want to try is 1, because that's very easy to plug into the natural log. And, you know, if I'm very sneaky, e squared is bigger than e and would be a good thing to plug in because the natural log of e squared is 2. All right, so on top I have, okay, so let's plug in 1 first. 2 minus 0 is 2 over 1. That's positive. And now if I plug in e squared, I'll have 2 minus 4 is a minus 2 on top, and on the bottom I have e to the 4th. So a negative over a positive is a negative. Now I'm just doing these in my head, getting these signs. You can stop and actually plug in your calculator to get decimal approximations because it only matters whether we have a positive or a negative. All right, I have a tangent line at E because my first derivative exists at E. So I have a point of inflection at E comma something. So let's see if I can summarize everything we know so far. From the first derivative test, I know my function should be increasing from 1 to infinity. I know my function should be decreasing from 0 to 1. Because of that, I'm going down and then up. I know there's at least a local minimum at 1. I know that I am concave up from 0 to E. I know I'm concave down from E to infinity. And there's a point of inflection at E comma some y value. And let's go on and find that y value. I find y values by plugging back into the original function. The natural log of E is 1, and 1 squared is 1. So there's a point of inflection at E comma 1. The local minimum happens at 1, and if I plug a 1 into my function, I get the natural log of 1 is 0, and 0 squared is 0. So I know that local min happens at 1, but is actually 0. The local min of 0 happens at x equals 1. Well, I'm supposed to find intercepts. 1 comma 0 is my x-intercept, and it's a local min. And now I'm curious about what happens as x approaches 0 from the right-hand side. Well, if I think about the natural log function, it looks like this. As natural log approaches 0 from the right-hand side, I go to minus infinity. Well, I'm squaring those y values. So instead of going to minus infinity, this is going to go to positive infinity. All right, let's see if I can put it all together. My function decreases until I get to x equals 1, and there's an asymptote at 0. So I know my function goes down from that asymptote to there, and that's not a realistic shape yet, but I'm just trying to get an idea of it, and I know I'm supposed to increase from 1 to infinity. Something that looks like that. And so now I just need to see if I can figure out the shape. So this is supposed to be x equals 1, so that would be x equals 2 and 3. And I know I have a point of inflection at E comma 1. And that between 0 and E, I'm supposed to be concave up. So that shape would look like this, with that vertical asymptote on the y-axis. And then after that, I'm supposed to be concave down. And so there's my more realistic shape. And I'm just curious, let's use our calculators and see if we did a pretty good job. So here on the standard viewing rectangle, I see that going down and then doing that kind of subtle turn there with that point of inflection at E. I'm going to zoom in a little bit and see if I can get a little bit better of a picture. And then I'll probably post either a Wolfram alpha graph or a GeoGebra graph when I'm all done. Let's change this spot just a little bit. All right, and about E, I should see a point of inflection. I don't have it graphed high enough. I'll show you a better picture and I'll link below. But there is your author's graphing procedure, and I should say one more thing. Now that I've graphed everything, I can look at my local minimum and tell you for sure that it's actually an absolute minimum. And that makes me happy. All right, there's your author's graphing procedure where we connect all of the things we've done so far.